So yeah, so we're starting the 10.3 potential divider MCQ segment today. We're going to see some problem from here. Most of the problems are pretty simple. They are all based upon the basic formula for the potential divider circuit, which looks like this. That if we have a source of a supply voltage V, and if we have two resistors, let's say R1 and R2, one of them can be fixed, the other one can be variable. This one could be a thermistor, this one could be an LDR, doesn't matter. And if we have some wires coming out of these parts and connect voltmeters over here, let's say these are voltmeter 1, this is our voltmeter 2. We have connections like these. By changing the variable resistance, we can actually change the output of these two values. So the way it works, that voltmeter 1 will give us the fraction of voltage of the supply, which will be divided in terms of the resistance in series. So I can write R1 divided by R1 plus R2 whole into V. This is the reading for the voltmeter 1. This will be give us the readout for R2 divided by R1 plus R2 into V. This is a very basic format. If we have some additional component, let's say if we have, let's say, one component of another resistance, let's say over here, let's say that is a fixed resistor that is not part of the potential divider circuit, but it just exists in the circuit, that is R3. This will simply get added at the denominator. It means that the total resistance of the circuit is R1 plus R2 plus R3. R1 resistance will get the fraction of this much of the whole total. R2 will get this much of the total. That's one way to go for it. The other version for the potential divider circuit can look like this. If we have a source, let's say we have a source of voltage, supply voltage V, and we have a long resistance wire, which is shown like a very long resistance like this. And we have two outputs on two sides. No. We have two outputs on two sides like this. And we have a movable contact. A movable contact, which can be also said to be a jockey. Let's say that movable contact is right here. Sometimes movable contacts are shown by a bit of an extended wire. So we have a bit of a curve over here. And then if we connect two voltmeters over here, let's say voltmeter 1 and voltmeter 2, the readings of these two things will be dependent upon the resistances of R1 and R2. So, or in other words, it will be located based upon the position of this jockey. If you move the jockey higher, R1 will become smaller, R2 will become equally bigger, and vice versa. So the ratio can look like this: R1 divided by R1 plus R2 into V. Here the ratio can look like R2 divided by R1 plus R2 into V. It's that simple. However, because we already know from our O-levels chapters that resistance of a conductor is directly proportional to its length. So, and this is a single long wire, uniform piece of wire with uniform resistance distribution all over. So if we can somehow measure the length of this conductor, depending upon the position of this jockey, let's say if this length is L1 and this whole length is L2, and we can essentially replace this expression of resistance in terms of length, because these two variables are directly proportional. So we can write over here, this can be also written as L1 divided by L1 plus L2 multiplied by V, or this can be written as L2 divided by L1 plus L2 into V. You have to understand that resistance and length are not equal, but the ratio of resistances can be equal to the ratio of lengths, because there is a proportionality relationship. So this is also an useful expression for measuring fractured voltage out of a large supply. And that's pretty much it. And there is one more thing that is called measuring the potential difference across 2 points of a circuit, which we're going to pick up some question and see for a specific example. For that, I mean, if we jump into the question, have a look. Question number 1, it says a potential divider is used to give outputs of 2 volt and 3 volt from a 5 volt source. As shown, what are the possible values for the resistance of R1, R2, and R3? So I'm going to take out this question and discuss this thing in detail. So let's say we're going to paste this question over here. So let's have a look. Okay. The first thing you need to understand that we have connected a voltage supply over here, which has a 5 volt source, and this is the 0 volt level, which means here the potential is 0. So this 5 volt would be available, used across these 3 resistors. You can see that this is the 0 volt level. From here to here, this has a value of 2 volt, which means this resistor is basically consuming 2 volt. From here to here, the difference is 1 volt, which means this resistor will be consuming 1 volt. That's the difference between the two ends. not the absolute value. The total voltage across these 2 points is 3 volt, because this is 0 and this is plus 3. But that's not essentially important for us, because we're trying to figure out how much is the individual voltage consumed by each individual component. So I'm going to rub this off. And because the source is of 5 volt, essentially we are spending 2 volt here, 1 volt here, so the remaining should also be 2 volt. So the ratio of the voltages is 2 is to 1 is to 2. Since these components are in series, if you consider the formula for V equals to I at the Ohm's law, because they are in series, the current through the component should be a constant, which means in this case voltage should be directly proportional to resistance. So this is the ratio for the voltage. I'm not giving equals to, I'm giving an arrow because this is just a ratio, which means the resistance of the ratio should also be in terms of 2 is to 1 is to 2, because V is proportional to R. We can say it for a series combination. So we now have to find out in this whole option choices that which of this ratio give us this ratio for the R1, R2, R3 values. So check it out. We have 2, 1, 5 doesn't match. 3, 2, 4, 2 doesn't match either. 4, 2, 2 can give us 2 is to 1 is to 2, which seems to make sense. 4, 6, 10 also doesn't match. So C is the only possible answer. That's for question number 1. That's the decision that we can take. The only reason with this circuit could work like this is because the I was a constant for a series circuit. That's why this equation could be, this proportionality could be built up. But this is not a generalized format for every question. The procedure for individual question can be different from one another, which we're going to see for multiple other examples. Let's have a look at this question. There is something to understand from this question, because it's something a bit new for your content. You haven't seen this kind of a question in your O levels. Let's have a look. The diagram shows a potential divider connected to a 9 volt supply of negligible internal resistance. What range of voltages can be obtained between P and Q? Important bit. What range of voltages can be obtained between P and Q? Now, here's the deal. Have a look. This is a 9 volt supply. We have a 10 kilo ohm fixed resistor, and there happens to be a variable resistor which is a labeling of 50 kilo ohm. Now you might wonder, if we say this is a variable resistor, what does this 50 kilo ohm mean? A variable resistor is supposed to have variable resistance. So what does this 50 kilo ohm means? If in any case you see a labeling beside a variable resistor, you would always understand this is the maximum resistance of that variable resistor, which means if you set it to a maximum resistance, this is going to be 50 kilo ohm. The minimum is always 0 ohm. Minimum resistance of a variable resistor is always 0 ohm. You should remember from the potential from the variable resistor rheostat that I showed you the earlier day for the sliding contact. If we push it all the way to the left, there's gonna be zero resistance across the two terminals. So minimum resistance offered by a variable resistor is always 0 ohm. This is a default thing, and the labeling will always give us the maximum voltage. Now let's try to figure out what are the possible voltages that we could possibly get. So let's take one at a time. If we set this if we set this rheostat at 50 kilo ohm, then we're going to have 1:5 ratio of voltage. 10 kilo ohm is to 50 kilo ohm is 1:5, which means the PQ value in that case, so voltage across PQ can be 50 divided by 10 plus 50 into 9.0. Not to the power, it's multiplied. Looks bad. I might as well choose a bit smaller thickness, maybe 9.0. So this would be 5/6 of 90, 9.0. 6 into 1.5, so 7.5 volt. So the maximum voltage that you can get is 7.5 volt. What is the minimum voltage that you can get? The minimum voltage is always 0 ohm. So you do understand that if we set this thing to at zero resistance, essentially this will not produce any resistance at all, and it will not produce any potential drop either. So in that case, all the 9 volts would be applied across this 10 kilo ohm resistor. So idea is this: if we start the variable resistance from 50 kilo ohm and slowly start to reduce this voltage, the output across the PQ point, let's say this is a voltmeter PQ, this value will slowly become smaller, and the remaining voltage would be available across here. So as this one's voltage becomes smaller, this one will essentially consume bigger and bigger fraction of the voltage, because the sum of these two components voltage will always be equal to 9 volt. That's how a series combination works. So eventually when the resistance of this component will become 0, this drops to 0. The voltage echo consumed by this component will also become 0. Essentially, in that case, the voltage of the 10 kilo ohm will become 9.0 volt. So the question over here asks that what range of voltages can be obtained between P and Q? So range essentially means from the very smallest value to the very highest value. The possible minimum value we can get over here is 0 volt. The possible maximum we can get over here is 7.5 volts. So hence, B is the only correct choice.
স্যার আমাকে কি 7.5 ভোল্টসটা কেমন ভাবে মোটা আরেকবার বলবেন?
7.5 ভোল্টটা হলো যখন আমরা এই ভ্যারিয়েবল রেজিস্টার ম্যাক্সিমাম রেজিস্ট্যান্স দিয়ে সেট করব, বিকজ উই আর ট্রাইং টু ফাইন্ড আউট দ্য পসিবল ম্যাক্সিমাম মিনিমাম ভোল্টেজ অ্যাভেলেবল। দ্যাটস ওয়াই উই আর trying to use the two terminal values of this variable resistance. The label value is the maximum resistance of the variable resistance, and the minimum resistance of a variable resistance is always 0 ohm. This is by default. So if this variable resistance is set as 50 kilo ohm, then we have two components, R1 and R2. So we use that ratio of R1 plus R2 divided by R1 plus R2. So 50 divided by 10 plus 50 into 9.0. 9.0 is the source voltage. So you get the fraction, you calculate out 7.5 volt, which means that when this variable resistor is set at its maximum resistance, 50 kilo ohm, namely, then the available voltage across these PQ terminals will be 7.5 volt.
আচ্ছা স্যার।
All right. আচ্ছা, তোমাদেরকে আমি আরেকটা কোশ্চেন বলি। এই কোশ্চেনটা অ্যাকচুয়ালি তোমাদেরকে ওইদিন পড়ানোর সময় আমি জিজ্ঞেস করতে ভুলে গেছি। Kids, have a look at this question. This is not from the MCQ paper. I really want you to understand and tell me what is happening. Let's say this is a battery. Let's say voltmeter 1. Here we have a switch. Here we have a resistor. We have voltmeter 2. And then we have a capacitor. That's a voltmeter 3. I think this MCQ is going to show up after a while. I'm not sure if it does show up. It's just something that I want you guys to understand. That's why I'm showing you this thing right now. All right. At the initial case, hear me out, because I'm going to be asking a question and I need you kids to respond, whether you share your answers with the class or not. At least share with your own self. That helps. When the switch is open, initially the capacitor is uncharged and the battery has some voltage. So when the switch is open, what will be the reading of these 3 voltmeters? Let's say the source voltage is 9 volt. When the switch is open, what would be the reading of these 3 voltmeters? V1 gives you how much? V2
স্যার
gives you
9
how much? And V3 gives you how much? Okay, V1 gives you 9 volt. How about V2 and V3?
0
And
0
all right, that is appropriate and correct. Whenever the capacitor is discharged, there is no charge in the capacitor, the switch is open, these are the readings we're going to get. Now comes the question. Try to understand very carefully. If we now close the switch, and what would be the reading the moment we close the switch? What would be the reading the moment we close the switch? Just to bug with your brain, I forgot to connect one component over here. I would like to show you something. It has a small bit of variable resistor. Sorry, not variable resistance, internal resistance. This source has a bit of internal resistance. So at the moment of closing the switch, what should be your readings? What should be the value of V1? What should be the value of V2? What should be the value of V3? The moment you close the switch, the instance you close the switch, what do you get?
V1 তো 9 থাকবে না।
That's what you need to ask yourself. Do you guys remember how does a capacitor work? Before I tell you the answer of this thing, I would like to show you how a capacitor works for a much simplified circuit, because something that you need to understand. This is how a capacitor works. Have a look. Let's say we have a simple cell battery of 6 volt. Let's say this doesn't have any internal resistance. We have an open switch and we have a capacitor over here. Initially, the voltage across the capacitor is 0. It's an uncharged capacitor. Try to understand. The moment we're going to close the switch, what's going to happen? Electrons are going to start traveling from this negative end to this end of the battery, to this end of the capacitor. So this end will slowly become more and more negative charged. And this end of the battery, positive end of the battery, is going to pull electrons out of this plate of the capacitor. So electrons are going to travel from here to here, and this plate is going to slowly become more and more positive. And the one thing you should always know that 1, 2, 3, 4, 5. So let's keep on more here. One thing you should always know that a battery always works in such a way that it always gives up and accepts equal number of electrons. It pulls electron from the positive side and gives out electrons from the negative side. At any point of time, the battery is truly never charged. Truly charged means a battery never suffers from excess of electrons or shortage of electrons compared to its proton numbers. It always experiences equal number of protons and electrons existing within itself. But because of the chemical reaction that happens within a battery, it always separates electrons on one side, pushes them on one side, which is the negative side of the battery, and the other side becomes positively charged because of shortage of electrons. So that's how a battery works. So if we have, with the over duration of time, let's say 1000 electrons come out of here, this side will essentially pull in 1000 electrons, which means this plate, this capacitor will become charged. Now you have to understand this thing. Take a good look. This was the capacitor, this was the source of fixed voltage supply, 6 volt. This will not change over time. But this capacitor, when the switch was open, had a voltage of 0. As time goes by, its voltage will increase, right? Let's say from 0 volt, just from 0 volt, it will become 1 volt, then it will become 2 volts, it will become 3 volt. It will slowly increase. What will happen as it slowly increases? What will happen as it slowly increases? Try to understand. Here we have a positive end of the battery, and here we have the positive end of the capacitor. This capacitor will essentially try to inhibit or oppose the flow of conventional current. This is going to work very much similar, not same, very much similar, as if one of these opposite cell is connected to the circuit. Something like this. We told you about this combination in our earlier class, and you are very much correct in your guesses or in your understanding that if we have a combination like this, the total EMF across this whole battery will be this one minus this one, because they are connected in reverse polarity, opposite polarity. So this is the case for a fixed supply where the EMF of the battery and the cell, they are constant to each other. Constant to not constant, they are constant, not to each other. They are constant. But the voltage across the capacitor is not constant. Over time, the capacitor becomes more and more charged, the voltage across the capacitor increases, which means that the current flow, the effective EMF, I'm going to use this term, effective EMF. Hello, assalamu alaikum. जी भाई आवाज आ रही है? Sorry, my food got delivered. So as time goes by, the voltage of the capacitor will slowly increase. So this is very important for you to understand. As the capacitor's voltage increases, this is something similar, but not same, something similar, as if we're going to connect more opposing voltage in this circuit. So but we're not going to add one cell after another, because let's say if the value of one cell is 1.5 volt, you cannot simply increase the opposing voltage from 1.5 volt to 1.6 volt. You just, by attaching another, you see, will simply, this is not going to happen. If you attach two of them in opposite polarity, you're simply going to jump from 1.5 volt to 3.0 volt. That's what you can do, because batteries or cells come in a fixed amount of EMF. But that's not the case for the capacitor. The capacitor slowly charges up as like temperature, or like the flow of time, like a continuous variable. So it was initially at 0 volt. It is going to slowly charge up from 0 volt to higher value. I'm not drawing the curve because it has a negative exponential behavior. Do not want to get into that. But as the capacitor slowly charges up, it slowly is going to try to give an effective EMF that is smaller. So the effective EMF of the circuit can be written as 6.0 volt minus the voltage of the capacitor. That's the effective EMF of the circuit. As this one is going up, the effective EMF is going to go down, which means the actual current flow through this circuit is going to become less. Now you might wonder, why should that happen? I mean, shouldn't this kind of shouldn't there be a very large current at the beginning and eventually it will be zero? Well, for an ideal case, the current will be infinite and the capacitor will be charged in 0 seconds. For an ideal case, but well, whenever we have to deal with infinite current, we bring about some restrictions. Let's say just to limit the current, we have connected a resistor over here. So what's going to happen? Initially in this circuit, we're going to have 6 volt effective EMF. As time goes by, the effectiveness is going to decrease, and this resistor has a constant, so V equals to IR or I equals to V by R, which means as the effective EMF of the circuit decreases, for a constant resistance, the current will also decrease, which means the capacitor will then start to charge up slowly. So initially it will charge up faster, later it will charge up slowly. But as the capacitor slowly charges up, ultimately given enough time, and the final voltage of the capacitor can reach up to the source voltage. This can happen. This is achievable. At that point, the current in this circuit will be zero. So this is going to happen if we allow this circuit to run for a significantly long duration of time. That's why in this question, in this upper question that I was discussing over here, that at the moment of closing the switch, what should happen? At the moment of closing the switch, V3 would still be zero, because you have to understand that there hasn't been enough time passed by so that the capacitor can have stored any charge. So the V3 will still be zero. What is gonna happen to V1 and V2?
Sir, V1 to 9 থাকবে.
Now V1 কি আসলে 9 থাকতে পারবে? আচ্ছা, just for the sake of understanding, let's say এখানে মনে করো এই ক্যাপাসিটরটা নাই, ডিসরিগার্ড দিস ক্যাপাসিটর। আমি এটাকে কোনোভাবে কাটা বের করে ফেলতে পারবো? ক্যান আই ডু দ্যাট? দাঁড়াও দেখি লুপসের দিয়ে আমি এটাকে কাটতে পারি কিনা। মনে করো আমাদের ক্যাপাসিটরটা এখানে নাই, cut. Let's say the capacitor doesn't exist for the time being. We just have a circuit which is closed. Just at the moment of closing the switch, current is going to start to flow. এখানে আর at the moment applicable না, because now the capacitor is off নয়. So let's say when the switch is closed, at the moment কেটে দিলাম, পরে আবার আমি কন্ট্রোল জেড দিয়ে সব কারেক্ট করব. When the switch will be closed, what will be the reading of V1 and V2?
9.
Less than 9.
It should be less than 9 because of this. Remember, V1 equals to terminal voltage when I is not equals to 0. When the switch is open, there is no current, so the EMF is the V1. Simple. But the moment you close the switch, there is a bit of a current, which means the total EMF of the circuit of the battery is going to be divided as V plus V, or I can write I into R, which is spent over here, plus I into smaller, which is the lost voltage. Because of the presence of this internal resistance, this battery will spend some voltage within its own self for being able to run this current through this external circuit. That voltage will be lost and it will not show anywhere in the circuit, which means the reading of this thing will become somewhat less than 9. Just for the sake of example, let's say now this voltmeter is giving us reading of 8.0 volt. It will be somewhat smaller, but just to make numbers involved, let's say when the switch is closed, this is 8 volt. In that case, the voltmeter 2 will also read 8 volt. You can never get voltmeter 2 to give you a true 9.0 volt, because as long as the current is flowing by, all that you can measure is the terminal voltage. You cannot measure the EMF. When a current is present, this product will be non-zero. As a result, this will always be smaller than the EMF of the actual cell or battery. Some portion of the EMF will be wasted or will be used up to overcome the internal resistance. এই কনসেপ্টটা বুঝা গেছে কিনা? এই পার্টটুকু বুঝো।
Yes, sir.
Everyone agree on this one? Does it make sense?
Yes, sir.
যখন কারেন্ট থাকবে না তখন ইএমএফ মেজার করবে, যখনই কারেন্ট থাকবে তখন ইএমএফ থেকে একটু কম মেজার করবে, কারণ ব্যাটারির ভিতরে একটু ইএমএফ এর একটা পোর্শন অটোমেটিক্যালি খরচ হয়ে যাবে, যেটা বাইরে এক্সপোজ হবে না, ব্যাটারির ভিতরে ওটা খরচ হয়ে যাবে, ওটা ইন্টারনাল লস হিসেবে চলে যাবে। এখন মনে করো আমরা ক্যাপাসিটরটাকে আবার ব্রিং অ্যাবাউট করব। সো আই সেভ ইট ইন মাই কন্ট্রোল সি, লেটস সি ইফ উই ক্যান ব্রিং ইট আপ in a simpler version. Control V, and can we move it? Well said. Let's select it by this thing, the whole thing. Okay, and we bring it up right here. Beautiful. So let's say now we have brought about the capacitor once again. Now let's forget about this cross sign. Let's say this line doesn't exist. Delete. Okay. Now try to understand. At the moment of closing the switch, the capacitor will still read 0 because there hasn't been enough time for the capacitor to be charged. But what should be the reading of V1 and V2? Now, I don't want you to give me numbers. Forget about this number. Disregard that. Let me erase it. I want you to give me these two answers, V1 and V2 reading, in terms of equals to 9, more than 9, less than 9. Just use
Less
those
than
terms.
9.
Sir, less than 9.
Both of them should be less than 9, or should one of them be less than 9?
Both of them will be less than 9.
Both of them would be less than 9. So less than 9.0 volt. এই লজিকটা সবাই বুঝছো কিনা? কারণ ব্যাটারির ভেতরে কিছু কি হচ্ছে, ভোল্টেজ খরচ হয়ে যাচ্ছে। আচ্ছা, এখন আসো, now let's say we allowed the circuit to run for a significantly long time, so long after switch is closed. এই কন্ডিশনে আমাদের রিডিং গুলো কত কত হবে? V1 equals to কত হবে, V2 equals to কত হবে, and V3 equals to কত হবে? Long after, let's say significantly long after. Let me give you a little bit of help. What I explained right over here. I told you that if given enough time, ultimately the voltage of the capacitor and the supply will become equal, and the current in the circuit will become 0 because they'll be equally opposing each other. So now think about it. What will be the reading of these three voltmeters long after the switch is closed?
Sir, V3 help will check in 9. V1 will become 0.
V1 and V2 will be.
V2 tech.
I'll help. I'll write this. See if that helps.
V2 0 হয়ে যাবে।
So সবই 0 মানে
So shouldn't V1 and V2 be less than 9, and V3 will also be less than 9, but it will be negative?
Well, whenever I say long after, I mean that enough time has passed by for the current to become effectively 0. It will theoretically, it will never become perfectly 0 because the graph becomes asymptote. So what you said is absolutely correct. I mean, to its fullest is precisely correct. But the way your examiner, say people, like to see is that whether you have a practical understanding of this thing or not. So the way this is the version that they appreciate from the students, that long after the switch is closed, current in the circuit will become 0 because of the opposing voltage from the capacitor. The EMF of the battery and the voltage of the capacitor will become equal. So this is what the CAE people or the examiners of CAE appreciates. Let me show you this. No, don't clear canvas. How can I rub this? Acha, এটা আসলে input report dependent. Okay, never mind. So this your CA examiner is like this, that long after the switch is closed, the current becomes 0, which means if you consider that this is a resistance of R, if the current is 0, so if you try to measure the potential difference across it, what you're going to get? V equals to IR. If current is 0, what you're going to get? You're going to get 0, right?
Yes,
Think,
sir.
if the current doesn't exist, the potential drop of a resistor is essentially 0, which means V2 will essentially become 0 volt. And since there is no current in the circuit, so this part has also become 0 because current doesn't exist. So if you just multiply this thing, you will still have 0. So which means there is no longer any lost voltage inside the battery. So which means this will also become 9.0 volt, and this will also become 9.0 volt. Given enough time, you'll be able to achieve this. Does it make
Sir,
sense?
V1 টা 9 কেমনে হলো আরেকবার বলবেন?
V1 9 হওয়ার জন্য আমাদের কি লাগবে? এই যেটা বুঝো, V1 9 হওয়ার জন্য আমাদের এই ইন্টারনাল internal loss voltage যেটা মানে internal drop in loss voltage, we use the term loss voltage, this loss voltage has to become zero. What is the only way you can make the loss voltage? Loss voltage expression হচ্ছে I into internal resistance. Internal resistance is a structural property, we cannot disregard it. There is no way you can control this after the battery has been manufactured, you will have to deal with it. You cannot simply make it zero. It's a fixed number. Once the battery has been manufactured, it has a fixed value of internal resistance. All that you can do if you want to make this whole thing zero is to make this one zero. If you can somehow make this one zero, the product will become zero, right?
Yes, sir.
So if we allow enough time to flow to pass by, the current in the circuit will become zero because of the opposing factors of this one and this one. They will oppose each other's voltages, and the current will become essentially zero. As a result, the internal drop, internal resistance product or the loss voltage will also become zero. So now the EMF of the battery can be entirely exposed. This is very much similar as if the switch is open because there is no current in the circuit anymore, which means there is no loss voltage anymore. The internal resistance still exists, but because the current has become zero, the product of I into R has become zero, so the loss voltage is no more, which means the reading of this voltmeter will now give a perfect 9.0 volt. And it can be only achieved when the capacitor also has a voltage of 9.0 volt. Who was the other person said about the negative voltage? I forgot to say the name in the participant list.
Sir, it was me.
Yeah, Zarif. What Zarif proposed that this is going to give us a reading of 9.0 volt and this is going to give us a reading of minus 9.0 volt. This is absolutely beautiful because if you consider the same polarity of the voltage in just Kirchhoff's second law, if this one gives us a positive output, this should definitely give us a negative output because these two voltages are working in opposite to each other. So they're not the same polarity. But for most cases of your CAE questions, they don't bother about this minus sign, at least up till now. But mentioning that these two voltages would give us opposite reading in the voltmeter goes on to show that you really understand how this circuit is going to work.
Sir, V1 equals to current multiplied by internal resistance, right?
No, no, no. V equals to current multiplied by internal resistance. And capital V equals to current multiplied by external resistance. The sum of these two equals to EMF.
Then what does V1 equal to?
V, in this case, V1 is connected directly across the battery. So if there is some current, this reading will always be less than 9, somewhat less than 9. If there is no current, this reading can be perfectly 9.
আচ্ছা স্যার,
এক মিনিট, আজারি বুঝছো কি বলছি?
Yes, sir.
হ্যাঁ বলো, যারা বলো।
স্যার এখানে যদি ইন্টারনাল রেজিস্ট্যান্সটা না থাকতো তাহলে কি লাইক এট দ্য মোমেন্ট অফ ক্লোজিং দ্য সুইচ তখন কি V1 এ 9 হইতো?
যদি ইন্টারনাল রেজিস্ট্যান্স না থাকতো তাহলে এই জিনিসটা এক্সিস্ট করতো না, এই জিনিসটা এক্সিস্টই করতো না, which means your voltmeter reading will be always 9, like always 9. If there is no internal resistance, there is no cost or reason for loss voltage, which means you will always have a constant voltage reading across your source. If internal resistance would not exist, this will always be 9 volt, whether current flow happens or not, doesn't matter.
ওকে স্যার।
বলবান এই পর্যন্ত বুঝা গেছে কিনা? Up so far, বুঝা গেছে কি? I'm going to write one more equation to make sense with you. সেটা হচ্ছে, have a look. If you have a good look, I'm going to use green over here just to make a bit more visible explanation. Can I get rid of these circles? Uh, okay, I wanted to get rid of that circle. Have a look. This is your EMF source. I'm going to label this EMF source up to here. This is your EMF source, and there are multiple voltage eater, or we can say the locations where voltage is used up. So let's say those voltage eater, one of them is this one, one of them is this one, and one of them is this one. You have 3 locations where the voltage will be used. You have one location where the voltage is created, or what do you call it, EMF. So at any point of time, this equation will always hold true. The total supplied EMF is equals to the loss voltage plus the terminal voltage plus the voltage across the capacitor. This will always be true. Now, if current flow does exist, then this will be true. This will exist. If current flow does not exist, then this, some of these two would be true. So When the switch was initially open, when the switch was initially open, the EMF of the circuit was perfectly 9.0 volt. Internal resistance was zero. This was zero. This is also zero. When the switch was just closed, then this internal resistance would become slightly bigger than zero because it would now have a value. So the voltmeter reading, and this would still be zero because it didn't get enough time to become charged, where the voltmeter reading would be slightly less than 9.0 volt and the EMF would still be 9.0 volt. This is the theoretical EMF value. So this would be the reading out of the voltmeter 2. This will also be the reading of the voltmeter 1. So you would get the same reading for those two things. And after long enough time, after long enough time, this EMF would still be 9.0 volt, which is a true EMF. The internal resistance related drop or the loss voltage will also become 0 volt because the current will die out, and the terminal voltage will also become 0 volt. As a result, all of the voltage will be opposed by exclusively by the capacitor. So this is the sequence that by which it's going to happen. বুঝা গেছে কি?
Yes, sir.
All right. So let's go ahead and try to figure out some more MCQs. Uh, I want you guys to have a look at this question and see if you can solve this one. See if you can understand the content of question number 3. Have a look. If you need help, I'll help you. You can read from here or you can read from your MCQ worksheet if you have it in your hand. But try it.
ডি হবে।
D happens to be the correct response, but do all of you understand this thing? This is a very good conceptual question, which is important for you to understand, because in the actual exam, in the paper 2, I mean, in the paper 2, they could also give you the same question and simply ask you state and explain what will happen. 4 marks.
স্যার কি হবে এটার অ্যান্সার?
It correct answer হবে D. Let me explain why. And if I was answering this thing for a paper 2 question, for a structured question, paper 2, this is how I would write the answer. I'm gonna go slow. I want you guys to hear me out and try to process the information in your head. When the resistance of the variable resistor is decreased, comma, total resistance of the circuit decreases. So current flow increases, comma, ammeter reading increases, full stop. The voltmeter reading also increases because now the fixed resistor gets a bigger fraction of the battery voltage, or you can write battery EMF, because the variable resistance value got decreased according to the formula of potential divider. And I'm going to write the potential divider formula for this question in this format. Voltage across fixed resistor, so I'm going to write F equals to resistance of fixed resistor divided by resistance of fixed resistor plus resistance of variable resistor. The examiners can understand these terms. You don't have to explain, go ahead and explain which means what. Multiplied by the source. So I'm going to write this equation. So to explain how the voltage will increase, you can write this part, that because the RF got decreased, so this is going to get a bigger fraction. Or if you don't want to go it that way, if you don't want to travel in the path of the potential divider equation, you can explain it in a different way. So first you write what will happen to the current. First we write what will happen to the current, and then you simply go ahead and write because the voltmeter is connected across a fixed resistor and current value increases, so I into R also increases. So voltmeter reading increases. I'll say this again. Because the voltmeter is connected across a fixed resistor and the current value of the circuit increases, which you explained earlier, so the product of I into R also increases, comma, voltmeter reading increases. বুঝা গেছে কি?
Gee, sir.
Yes, sir.
Everyone?
Yes.
I'm going to explain the question number 4, and I'm going to do one thing because there are two similar questions about question number 4. So I'm going to place them side by side to boggle up your brain. And I'm going to give you some time, actually give you some time to figure out the two questions that I'm now going to place one after another. For those who have tried this MCQ, you might actually know what these two MCQs are about, but I always don't miss the opportunity to make this thing to my students. So I'm going to just do that. These two questions are amazing, and they are amazing because of their virtue. Should I place them side by side or one after? I think side by side is better, right? Yes, side by side is far better. Let's put it here. This one a bit smaller, maybe. Here. This one over here.
Sir,
Yes.
স্যার ভোল্টমিটারটা কেন ইনক্রিজ করে আরেকবার একটু বলতে পারবেন প্লিজ?
For that question, what I said that earlier, I just explained that I increases, right?
Yes, sir.
The voltmeter reading over here will be given by I into R, Ohm's law.
Yes, sir.
R is a constant because it's a fixed resistor. So if I increases, the product of I into R must increase.
আচ্ছা আচ্ছা স্যার বুঝেছি।
Beautiful.
Thank you, sir.
So I'm now placing these two questions in front of you. These are two different questions showed up on two different variants of the same year. I want you to try these two questions and figure out what is the correct response. You have 2-3 minutes. And pause the recording to give you the time. All right, that's enough time to look out for the solution. Try and tell me what will be the answer of these two questions.
রাইটেরটা এ হবে।
That is the correct response. So right এটা A হবে আর left এটা
B হবে।
left এটা B হবে. That is also a correct response. Now the question is why. Let me explain my version. For those who are correct, I really appreciate you. Thank you very much. For those who couldn't solve it, hear me out. What you can see over here that this connection point, this slider, is basically dividing the P resistor into two parts, the top part and the bottom part. If we place the slider all the way up, the voltmeter will be practically connected to the two ends of the battery. You'll be having a reading of 4 volt, complete 4 volt. If you slowly slide it down, eventually you can connect it at the position X. When this slider will be connected at position, it will be connected at the position Y. When this slider will be connected at position Y, you will be only connected, the voltmeter will only read the voltage across this part of the circuit. Now this part of the circuit of the voltage basically means that this one resistor circuit, because this part is simply a connecting wire which doesn't have any resistance. The question also told us that both of these resistors had the same resistance, 10 ohm, 10 ohm, which means when this is basically bottom to the bottom, this one will give you a 2.0 volt and this one will give you a 2.0 volt. So the voltmeter reading will give you 2.0 volt, which means at position X, you'll get 4 volt. As you're going to slowly pull it down all the way up to Y point, it's going to reduce up to 2 volt. So B is the correct response for this question. এটা হচ্ছে এই question answer, which is very simple to answer because it's a good one. This one is an interesting one. Now, to make sense of this one, let me just show you one thing. Have a look at this circuit and try to answer this question. Let's say we have ideal components. This is a battery of, let's say, 6.0 volt and we have two resistors. One is, let's say, 1 ohm, and the other one is, let's say, 2 ohm. So you can very well guess what will be the voltage across these two resistors. So what will be the voltage across this resistor? What is the voltage drop across this resistor? Divide 6 in 1:2 ratio. You should be, that should be easier to do. So this one,
Tricorder.
this one should get the voltage reading for this one should be 1 divided by 1 plus 2 into 6. The voltage reading of this one should be 2 divided by 1 plus 2 into 6. So this will give you 2 volt, this will give you 4 volt. That's simple. How about we now connect a actual voltmeter across this voltmeter, across this resistor, and place it like that? Well, obviously the voltmeter reading of this one is going to be 2 volt, no big deal. Consider everything as ideal components. Ideal components. Now, what if we connect another resistor over here that has a personal resistance of, let's say, 1.0 ohm? What would be the reading of voltmeter 1? This is a weird question because you have never seen this thing happen, because this is something that we never do. This is something that is not supposed to happen, but you have to understand what happens if something is connected in this manner. What is going to happen? Hear me out. What is the resistance of an ideal voltmeter? Resistance of an ideal voltmeter equals to how much?
Infinite.
Infinite.
Let's see if you add 1.0 ohm over here, OT, this one. How much do you get?
Infinite.
Infinite.
So should you expect any change of this reading?
No.
No.
Good. Now come over here. In this case, this slider was connected across this XY and the voltmeter was connected over here. What you really need to understand, take a good look. Because of the position of this slider, current will be flowing through this part, through the lower part of this slider, and through this connecting wire, and through this entire Q resistor, and come back to the battery. So current will be flowing in this pathway. This upper part of this resistor is basically getting connected in series with the voltmeter. Or in other terms, I can actually redraw this circuit in this manner. Let's say we have a 4 volt supply, and then we have a top resistor, we have a bit of a bottom resistor, and we have a bit of a large resistor over here. So this one over here is entirely Q. This over here is Py, where this top one over here is Px, and this one is connected with the voltmeter. Now have a look, see if it makes sense. The value of Py and Px can be changed depending on the position of the slider. If you move the slider up, Px will get smaller, Py will become bigger. If you move the slider down, Py will become smaller and Px will become larger. But irrespective, the Px part is practically connected in series with the voltmeter connection. Voltmeter. Do you see that?
Yes, sir.
Current will practically flow in this pathway. So no matter what happens, we can always say that the voltmeter over here is basically connected in across the source. There is a bit of a resistance over here, but this resistance getting added in series with the voltmeter practically does not change the purpose of this connection. So this voltmeter will always be reading whatever the voltage that is available across this point and this point, and that those 2 points practically means the 2 end of the battery. So the reading of this voltmeter will always be perfectly 4.0 volt and nothing else. So for this question, the correct response would be A. Even if we move this slider up and down, the voltmeter reading will always be a constant 4 volt, not any change. This is very difficult to appreciate or see in the first glance, because we always understand, or we always try to presume that having a variable resistor should give us some variation in voltmeter reading. Well, that's essentially true, but not for unique cases like this, because that variable resistor was not connected with the voltmeter. That variable resistor was having the jockey connected to the battery, which give us this interesting scenario. My offered discussion is over. I would take questions now. If any of you have any question after this one, I'll entertain that. Anyone? Anyone?
No, sir, no question.
Beautiful. So আমি এই দুটো এমসিকিউ একসাথে ডিসকাস করলাম কারণ এই দুটো এমসিকিউ একসাথে ডিসকাস করা ডিজার্ভ করে সেই জন্য। So we're gonna go forward and have a look at this question number 5. This is a good one. So let's have a look at this one. I'm gonna help you understand this question. A PD of 12 volt is connected between P and Q. What is the PD between X and Y? Now, there are many different ways, at least 2 or 3 different ways to solve this question. I'm going to show you the method that I personally feel easy to deal with. Assume that we're going to connect this with a 12 volt supply. So the way I appreciate or tell the students that consider one end has a voltage of plus 12 volt and the other end has a voltage of 0 volt. Zara, no. MCQ explanations are not available in the book. That's where we people, the teacher people, make money and make a living out of it. বুঝছে কি বলছি?
Yes, sir.
Okay. Sorry to say that, but that's the truth. So assume one of the end has a plus 12 volt, the other end has a 0 volt. Now we are going to try to divide this voltage across these two parallel combinations. So here we have a parallel branch and here we have another parallel branch, and let's just apply the idea of potential divider formula to figure out the voltage that this source is going to have. Have a look. 12 volt is going to be available across this whole branch. The ratio of resistance over here is 1:2. So 1:2 is the resistance ratio. So voltage ratio should also be 1:2, which means this component should have a voltage of 1. Let me use a single color, red. 1 divided by 1 plus 2 into 12. That will be the voltage output of this one. And this one should give us a voltage output of 2 divided by 1 plus 2 into 12. So this is going to be 4 volt and this is going to be 8 volt. এটা বুঝছো কিনা দেখো।
Yes, sir.
এই সিরিজ কম্বিনেশনটা লাইনটাতে আমরা পটেনশিয়াল ডিভাইডারের রেশিও অ্যাপ্লাই করলাম। সিমিলারলি যদি এই সেম জিনিস সেখানে অ্যাপ্লাই করি, লোয়ার পয়েন্টে আমাদের রেজিস্ট্যান্স রেশিও হচ্ছে 2:1। তার মানে যেহেতু এখানে অলরেডি 1:2 হিসাব করছি, সো আমি ডেফিনেটলি বলতে পারি যে এই পয়েন্টে এই পার্টে ভোল্টেজ কনজিউম হবে 8 ভোল্ট আর এই পার্টে ভোল্টেজ কনজিউম হবে হচ্ছে 4 ভোল্ট। নাও ট্রাই টু আন্ডারস্ট্যান্ড। If I try to use this plus 12 volt information and slowly travel through from P point through Q point, this is how it's going to work out. At this point, the voltage of this point is 12 volt. This 12 volt voltage is available for this entire wire. For this entire wire, we'll have a voltage of 12 volt. This resistor is going to consume 4 volt out of it. So the voltage of this point would be plus 12 minus 4. So the voltage of exactly this point would be plus 8.0 volt. I'm using the sign plus, still maintaining it because it will be helpful for us later. This would be the voltage of this point, X point. This one is going to consume the remaining 8 volt and ultimately this wire will become a voltage of 0 volt. So the voltage of X is coming plus 8.0. In the same manner, if you apply this for the lower branch, here we have plus 12 volt. This one is eating up 8 volt. So the voltage of this point Vy will be 12 minus 8 gives you 4.0 volt. That is the reading for that is the plus 4.0 volt. This is the voltage for this point. And the voltage of this point, and then this one consists of the remaining 4 volt. As a result, this wire becomes 0 volt. So we now have the individual voltage values of Vx and Vy. So if you connect a voltmeter across these 2 points, you're going to get the difference of these two numbers. Difference of these two numbers happens to be 4 volt. P is the correct response. প্রসিডিউরটা বুঝা গেছে কিনা?
Yes, sir.
এই ক্যালকুলেশনটা যদি প্রপারলি বুঝো, you would always be able to solve this kind of problem no matter how many resistors are connected no matter how many branches are provided. I'll give you a problem right now. So I want you kids to copy this circuit that I'm going to draw right here in your copies and attempt this calculation actually with your calculators and come up with some value. Whenever these questions will come up as MCQs, the ratio of the resistors are always given in such a way that you can do that division of voltage in your head. Mentally, you can do that division. So I'm going to try to keep that simple. Let's say we have a battery of 12 volt. 12 is a number that has a lot of factors, good factors, 2, 3, 4, 6. All of them are factors of 12. So let's say we have some branches over here. So let's say this is our one branch. These are another branch. So we have 3 resistors over here. And let's say we have 2 resistors over here, and let's say we have another 3 resistors over here. Let's say the resistance of these resistors are 2 ohm, 4 ohm, 6 ohm. And then let's say over here we have 4 ohm and 8 ohm. And let's say over here we have 3 ohm, 6 ohm, and 3 ohm. Let me name some points. Let's say this is our point A, point B, this is point C, this is point D, and this is point E. Did you draw up this circuit? মানে সার্কিটটা তো বোঝা যাচ্ছে।
Yes, sir.
Now my question is that if we connect voltmeter across multiple different connection points of the circuit, let's say if we connect a voltmeter across AC, so what will be the reading about AC? What will be the reading about across CE? And what will be the reading across AD? I want you kids to try these 3 questions. Attempt, then I'll help. Once again, assume that this positive plate has a voltage of plus 12 volt, and assume this one has a voltage of 0 volt. And then you slowly start to reduce that number, and find out the individual voltage drop of these components. That will make the process far too easier, in my opinion. So try this. I'll help you after a while. I'm pausing the share recording because I don't want the waiting period in the video. So let's start recording. Like I said, that if any question is given in the MCQ, they would always give you such kind of resistor values so that it's easily doable for you. Have a look. Here the source is given as 12 volts, and all of these individuals parallel combinations have a total combination of 12 volts as well. So the applying the ratio is very simple. 2 plus 4 plus 6, 12, 4 and 8, 12, 3, 6, 9, also 12. Which means you should understand that each of the ohms would be consuming exactly equal to their voltage value. So here I'm assuming that the positive plate has a voltage of plus 12 volt. So within this branch, plus 12 volt will be spent altogether. So 2 ohm consumes 2 volt, remaining is 10 volt, plus 10 volt is written. Then 4 ohm consumes 4 volt, remaining is plus 6 volt, written over here. B has a voltage of plus 6 volt, and 6 ohm consumes 6 volt altogether. So you have 0 over here, makes sense. Similarly, 4 ohm consumes 4 volt, remaining is plus 8 volt, used up over here, becoming 0. Similarly, 3 ohm consumes 3 volt, 12 minus 3 plus 9 volt. Then 6 ohm consumes 6 volt, remaining is 3, and 3 ohm consumes 3 volt, becoming 0. So if the MCQ question shows up, this will be easier like that. If it's not an MCQ question, they might actually come up with a different numbers, so that you actually have to put on your calculator to get fraction values out of them, which is also very much possible. But just because I was solving an MCQ question and I wanted to be easier for you to understand, not to trouble you for the calculator, that's why I set up numbers like this. And I wrote all of these numbers without touching the calculator because it was doable by without touching the calculator. A individual blue writing gulo বুঝা গেছে কিনা? Are all of these individual blue writing clear to all of us?
Yes, sir.
Then this
Yes,
value
sir.
will be very simple for you, like super easy for you. ঠিক আছে? Now I have written the symbol plus over here. If you want to skip the plus sign, no big deal. You can skip the plus sign. You can simply take that 2 volt, 5 volt, and 1 volt. MCQ question shouldn't bother you for this kind of things unless there is a special scenario. There happens to be a special case where plus and minus can actually prove a pretty important role, which you're gonna see after a while. But is this whole calculation clear to all of us completely?
Yes, sir.
আচ্ছা, এটা বুঝলে তাহলে আমাদের এই টাইপের প্রবলেমের কোশ্চেন hopefully ইনশাআল্লাহ প্রবলেম হবে না. So let's go ahead and try to find out some other problems. So let's have a look at this question where we have plus and minus voltage available. So we're going to see this question in detail. So let's magnify this. So have a look. Try this one. Before I tell you anything, try this one on your own. And then if you need help, I'll help you. But small heads up, Like before, consider this end to be plus 2.0 volt and consider the negative end to be 0 volt and slowly calculate your way down. This will always be very easy for you to work with. পারা গেছে?
করছি।
আচ্ছা, I'm gonna pause the recording for a while. VSQ SQ 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 মানে হচ্ছে 1.2 volt plus 1.2 volt. Now they're asking us V1 minus V2. তার মানে হচ্ছে plus 1.0 minus plus 1.2 minus 0.2 volt. I think C is the correct response. বলো দেখো বুঝা যাচ্ছে কিনা,
স্যার
বলো বলো বলো।
বিটুইন এস এন্ড পি আর বিটুইন এস এন্ড কিউ বলেছে, তাহলে ডিরেকশনটা উল্টা দেখে এটা নেগেটিভ হবে না?
Well, you could consider this. Even in that case, this is gonna be minus minus 1.2 and then this is minus minus 1.2. No, no, no. বলতেছি কেন, let me tell you why. Between S and P, essentially they mean that this voltage would be of a fixed number. You have to understand this thing. This plus 2.0 is something that I am assuming for the ease of my calculation. This is something that they did not say. So in according to their term, the voltage across SP or PS is the same thing. This is just a number. I assume the positive plate to be plus 2.0 volt. Some other student might also go in this way. Some other student or some other teacher might also prefer that consider the zero plate to be positive plate to be 0 volt, consider the negative plate to be minus 2.0 volts. They can also teach students in this manner. This is also perfectly all right. But I didn't do that. Do you get my point?
জি স্যার।
So whatever the plus and zero that I'm getting for these exact points are entirely based upon my predicament or my assumption. So that would not affect our answer. So voltage across SP or voltage across PS would have a single numerical value. So that's why I wrote over here as numerical values. It could also get rid of this plus sign over here if you wanted. But ultimately, if you do V1 minus V2, you're going to be subtracting 1 minus 1.2, ultimately giving you minus 0.2, which leads to answer choice C. বলবান এই ক্যালকুলেশনটা কেন করছি বুঝছো কি সবাই? এখানে কি করছি এটা? এই ক্যালকুলেশনটা বুঝে গেছে কি? I calculated what will be the voltage consumed in
Yes,
this
sir.
part, that is 0.8. So remaining is 1.2, which will be the voltage of this one, and the rest of the part simply follows through. All right, let's go ahead. And then we have this MCQ and this MCQ. These are pretty simple stuffs. Simple stuffs, simple stuff. এখানে খুব কঠিন কিছু নাই, এগুলো তোমার অ্যাটেম্প করলে পারার কথা, না পারলে আমি নেক্সট ক্লাসে দেখাবো, ডোন্ট ওয়ারি। 15, we will try for 15. তোমরা তোমাদের ওয়ার্কশিটে অ্যাটেম্প করো, 15টা ট্রাই করো, ট্রাই করে দেখো কত আসে। কোনটা আসছে কারেক্ট অ্যান্সার?
Sir, A.
এ ইজ দ্য কারেক্ট অপশন। বাকি সবার কি এ আসছে? দেখো,
Yes, sir.
this is actually pretty simple, but still, if you understand the basic, this shouldn't be difficult. I'm moving on. If you have any question, please respond, or we are moving on. Number 16 টা try করো. It's a good question. Which diagram shows a potential reverse circuit that can vary the voltage across the lamp? Apart from being able to find out the current circuit, I also want you, all of you, each of you, to be able to understand why the other three options will not be acceptable.
স্যার কত নম্বর করতে বললেন?
16.
সিক্সটিন কি সি হবে না?
16 এর কারেক্ট সি হবে, বাট এবিসি কেন, এবি আর ডি কেন হবে না, এটা কি বুঝতেছো ঠিক মতন?
No, sir.
আচ্ছা, let me explain the other this other part of the question that I asked you to understand. Let me help you understand. So look, the question says that which diagram shows the potential reverse circuit that can vary the voltage across the lamp. So we are trying to find out, figure out a circuit which is what actually works as a potential reverse circuit. C is obviously the correct candidate because it looks like a potential reverse circuit. We have a potential reverse circuit. There is a jockey over here. If we move this slider up and down, the voltage across the lamp would be effectively the voltage available for the lower part. So if you move it up, the lamp is gonna become brighter. If you move the jockey down, the lamp is simply gonna become dimmer. It's simple. Why these three things? These the other three things would not be applicable. Have a look. Option choice A cannot be applicable because in this case the variable resistor is basically connected in parallel with the bulb. You can see, you have to understand that if we have a voltage value for this supply, let's say 2.0 volt, and the bulb has an operating ampere current, operating resistance of let's say 10 ohm, then this branch will always pull a very fixed amount of current irrespective of the resistance of this variable resistor. If the variable resistor has a small resistance, there will be a large current flowing through over here, and the battery is simply gonna drain pretty fast. If the variable resistor has a high resistance, then a small current will flow through here, and the battery is gonna simply last longer. That will not anyhow affect the current that will be pulled by this battery, because to be honest, if you have a look at the circuit, the battery happens to be individually connected to the supply without the effect of the variable resistor. The variable resistor will simply make its own current along this line. So within this much path, the variable resistor will pull its own current, and obviously the current gets divided over here. The bulb pulls its own current, and the variable resistor pulls its own current. They are independent of each other. That's why you cannot vary the voltage across the lamp simply by the circuit. B number is an absolute weird thing. You can see over here that here this is the variable resistor, and essentially we do have a short circuit across the variable resistor. There is a connecting wire connected on the two sides of the variable resistor. So essentially the current will flow through this path. There is no reason the current should flow through the variable resistor, because this is a zero resistance path, this is a some resistance path. Current will always flow through the zero resistance path. So this battery, this bulb will simply glow using the entire voltage of the supply, and you just have a constant brightness of this bulb. This variable resistor is simply useless. What happens? What is happening for option choice D? Why is this? What's going to happen for option choice D? Let's have a look over here. In option choice D, it says that current is going to come up over here. It's going to get divided into two parts. and one part is going to flow through here, flow down through this path, and eventually come back to the circuit battery. The other part is going to come over here, get split once again. This part is going to flow through over here, flow through this part, and eventually come back to the battery. And the third part is going to flow through the battery over here. Once again, I want you all of you to see that these two circuits are practically not much different. For both of these circuits, A and D, the battery is individually connected or directly connected to the supply. Have a look at this part of the wire, this part of the wire, and have a good look at this part of the wire. Whether you have the internal zigzag or this whole part or not, the bulb will simply pull a fixed amount of current out of this cell, and it will always glow at a fixed brightness. Moving this one might control how much current flows through these two branches, which can also affect the total current drained from the battery or not. But that will simply not affect how much current is going to be flowing through a fixed supply, through a fixed resistor like a filament lamp. So that's why none of these other circuits are acceptable. বুঝা গেছে কিনা?
জি স্যার।
স্যার ডি এর পার্টটা আরেকবার বুঝাবেন?
ডি এর পার্টটা হচ্ছে I want you to see this part of the circuit very clearly. Let me just use a bit thicker line maybe. Yeah. Have a look at this part of the circuit. Whatever current that flows through the bulb is exclusively dependent upon the voltage of this battery and the resistance of this bulb. So the brightness of the bulb would not change. This battery, this bulb is practically connected in parallel with the voltage supply. So if you connect a voltmeter over here, what would be the voltmeter reading? Same as the cell.
Same as the cell. Yes, sir. বুঝেছি।
There you go. Over here we have the similar question of maximum minimum output. I don't find this interesting. Neither this one. This is also very simple. Okay. We just discussed this one, which is okay. 27. Unique question. Try this. This is 27 in your worksheet. Original question number was 38. 27. Lately, I've been thinking to start a secondary business of marriage media. I want to set up a Gotkali service.
হঠাৎ
It's important that people who are decided to go for a settled marriage find an appropriate person for their likings and choices.
ওটার দরকার কি, আমাদের ফ্যামিলিতেই তো আছে নাকি?
বুঝি নাই?
ওইটার আর কি দরকার, ফ্যামিলিতেই তো থাকে।
Well, get married and then After some years, we'll talk again. You'll understand what I'm talking about. Anyway, so which one do you think is the characteristic for this question? How do you think this 200 kilo ohm resistance of this voltmeter, which is a unique case, will be affecting the circuit? Now, let me help you to understand this part. Take a look. I'm going to give you a rule of thumb first, and then I'm going to explain why that rule of thumb works. If ammeters and voltmeters do have some value of resistance that ideal than their ideal other than their ideal value, which means ideal ammeter resistance resistance of an ideal ammeter equals to 0 ohm. Practical ammeter more than 0 ohm. Resistance of an ideal voltmeter is infinite ohm. Practical ammeter really high value. So you have to remember this thing. This is the rule of thumb that whenever some practical equipments, ammeter or voltmeter, gets connected to a circuit, their resistance will get added to the circuit in the way they are connected. Their resistance will get added to the circuit in the way they are connected. Let me elaborate this thing. For let's say this voltmeter connection, what's going to happen for this thing is that this 200 kilo ohm of resistance is going to basically come out as a new branch of 200 kilo ohm that's added in parallel with this 200 kilo ohm. And then this voltmeter is going to do its job as a voltmeter just fine. So you're simply going to have another 200 kilo ohm of resistance connected over here, not in series, because if it was connected in series, the voltmeter would still do just fine, because something plus infinite gives you still infinite. That wouldn't make any variation. Having a secondary branch as 200 kilo ohm over here, where these two numbers are both very large and comparable, which means the ratio of these two numbers is 1:1, which means half of the current is going to flow through this pathway, half of the current is going to flow through this pathway. So we're definitely going to have some change of readings. This is for the voltmeter. If it's an ammeter, you have to remember that we connect ammeters in circuit in series combination. So if some ammeter does have non-zero resistance, or they have some small resistance value, that resistance would simply come as connected in a series combination with the ammeter. So something like this. Let's say you have a circuit like this, and you have some resistor. This is a fixed resistor, and this is an ammeter, which the question says has some resistance of its own. So what will be the reading of this ammeter? So let's say if this is a 6-volt supply, and this is a, let's say, 10 ohm battery, 10 ohm resistor, and let's see if the ammeter also has a resistance of, let's say, 2 ohm, then the ammeter reading would be 10 ohm plus 2 ohm, that gives you 12 ohm. So what the way you should rephrase or see this ammeter can be something like this, that this ammeter's resistance would simply get added in the circuit as a series resistance of 2 ohm. So ammeter will simply do its job, and in the circuit there will be an introduction of 2 ohm extra resistance. So the total resistance of the circuit will become 12 ohm, and 6/12 gives you half ampere. So the reading of this ammeter will be 0.5 ampere. That's the way it works. So the question over here says a constant 60-volt supply is connected across the two resistors of resistance 400 kilo ohm and 200 kilo ohm. What is the reading on a voltmeter also of resistance 200 kilo ohm when connected across the 200 kilo ohm resistor as shown in the diagram? So if we have this thing, what will be the reading of this voltmeter? Well, it's pretty simple. This one has a 400 kilo ohm fixed, and this one has a common resistance of 100 kilo ohm. So now this the resistance will be the voltage supply voltage will be divided into 4:1 ratio. So this part should be getting 1/5 of whole into 60. So I get 12 volt. So A is the correct response. এই যে আমি ক্যালকুলেশনটা দেখালাম, ভর ভর করে অনেকগুলো কথা বলে গেলাম, এই ক্যালকুলেশনের কথাগুলো বুঝছো কে কে? না বুঝলে বলো, আমি আবার বুঝাই দেব। এনিওয়ান? সবাই বুঝছো তাহলে?
জি স্যার।
ওকে ডকে।
স্যার
বলো।
একটা অ্যামিটারের ভিতরে যখন কারেন্ট পাস করে তখন অ্যামিটারটা কারেন্টটা হচ্ছে মানে রেকর্ড করতে পারে, তাই না?
ইয়েস।
তো ভোল্টমিটার তা কি রেকর্ড করে?
Well, here's the thing. For realistic ammeters or practical ammeter or voltmeter to work, they both require some energy flow through them. I'm using the term energy over here because the emitter practically uses a portion of the energy of the incoming current or incoming charges and uses that energy to measure how much current is there. And a voltmeter also uses a small portion of the incoming current's energy and uses that energy to measure the voltage. This is how practical devices work. So they both use a portion of the incoming charges energy. So in other words, you can say that both of these components are responsible to change the circuit in some way. And if you, the reason I'm saying change the circuit in some way, because ideal emitter and ideal voltmeters are impossible equipments which work like magic. You connect an ideal emitter, you get the reading without spending any energy whatsoever. It will give you reading without making any change to your circuit. But that's not true for a practical emitter. Whenever you connect a practical emitter, your actual reading will drop by a little bit. Now that change of a current value might happen, let's say 5-6 decimal place after, because that's how an emitter is designed. It is designed to have a significantly smaller resistance compared to the lowest resistance of the entire circuit. You're gonna have some change in your emitter reading for practical emitters, but the circuits are usually designed in such a way that that change would not affect our 3SF values. Similarly, practical voltmeters does provide an additional parallel path to the circuit, but the resistance of the parallel path happens to be so large that it would affect your calculation of the circuit in the, let's say, 4th, 5th, 6th decimal place. So that change can be considered to be negligible. Does that answer your question?
Yes, sir. Thank you.
No problem. So let's give it a try for this one, number 30. কালকে আমি খুব অড একটা টাইমে তোমাদের ক্লাস নিতে যাচ্ছি, দুপুর 2টার সময়। করতে পারবা?
স্যার তখন স্কুল
স্কুল শেষ কয়টায়? স্কুল শেষ কয়টায়?
আড়াইটা
তারপর থেকে 3টা থেকে অন্য কোচিং শুরু?
না স্যার 3টায় নেই।
2টা আড়াইটা পর্যন্ত কি ক্লাস?
ফার্দার ক্লাস, ফার্দার ম্যাথস।
ফার্দার ক্লাস করা লাগবে, ফার্দার ক্লাস স্কিপ করার কোনো অপশন নেই। তাহলে কালকে ধরো 3টা থেকে 5টা বন্ধ দিই, কালকে 3টা থেকে 5টা বন্ধ তোমার ক্লাস করতে পারবে, টেস্ট ক্লাস।
সেটা করেন।
Yes, sir.
এভরিওয়ান, কারো ডিফিকাল্টি থাকলে আওয়াজ।
পারবো স্যার।
আচ্ছা ঠিক আছে, থ্যাংক ইউ ভেরি মাচ। দ্য ক্লাস ইজ নট ফিনিশড, আই এম জাস্ট স্কেজুলিং এ নিউ ক্লাস। সেটা হচ্ছে কালকে 3টা থেকে 5টা পর্যন্ত একটা ক্লাস থাকবে। তোমরা সবাই প্রেফারেবলি ইন্ডিভিজুয়ালি 2:45 থেকে আমাকে একটা করে ম্যাথস পড়ানো শুরু করবা। স্যার একটু পরে ক্লাস আছে, আপনি এসে ক্লাসে ছিলেন, সো দ্যাট আই ডু নট ফরগেট অ্যাবাউট ইট এন্ড আই মেক ইট হ্যাপেন। I am willing to take extra classes and finish this thing over, and I am willing to take regular classes as well. জিনিসটা হচ্ছে গতকালকে আমাকে একদিনের নোটিসে চিটাং যেতে হয়েছিল। I went to Chittagong in the morning bus, then came back at the night bus. So within 24 hours, I traveled from Dhaka to Chittagong and back. So yeah, kids grow up to embrace the adventures
থার্সডেতে
of
তাহলে
real
কি
life.
ছিল?
What?
থার্সডেতে কি ছিল?
Thursday রাতে?
না, থার্সডেতে বিকালে ছিল।
Thursday বিকালে কি?
স্যার ওই যে আপনি আমাকে বললেন না
5:30 to
আসতে না।
7:30
ও
ক্লাস ছিল।
আচ্ছা আচ্ছা আচ্ছা, থার্সডে বিকালে আমি পরের দিন সকালে বাসে উঠার যাবতীয় প্রিপারেশন কমপ্লিট করতেছিলাম, which went up to 2 a.m. at night, up till night.
সব ঠিক আছে তো স্যার?
That's a very elaborate question that you don't want the answer for. But let's just say, for this, because we are courteous and hypocrite people, yes. Let's try number 30. Let's not use we for an hypocrisy. I am a hypocrite person, so let's say yes. 30. A light dependent resistor R has a resistance of about 1 mega ohm in dark and about 1 kilo ohm when illuminated. It is connected in series with a 5 kilo ohm resistor to a 1.5 volt cell of negligible internal resistance. The light dependent resistor is illuminated in an otherwise dark room. So normally the room is dark, and now we're going to flash some bright light onto this every once in a while. So the light dependent resistor is illuminated in an otherwise dark room by a flashing light. Which graph best shows the variation with time t of potential difference V across R? So try to understand this question very carefully. There is a cell of 1.5 volt. In darkness, the LDR has a resistance of 1 mega ohm and about 1 kilo ohm in light. The fixed resistor is 5 kilo ohm. So try to understand this thing. When there is darkness, let me take this out. It's easier for me to explain. When there is darkness, the resistance of this thing in darkness, this resistance of this thing is 1 mega ohm. And in light, the resistance of this thing is 1 kilo ohm. You need to understand just by looking at these numbers that this is way too big compared to 5 kilo ohm. Am I correct? Like 5 kilo ohm and 1 mega ohm is like too big. So
Yes, sir.
in darkness, the resistance would be divided across them, or you can pretty much say that the resistance would be divided in 5 is to 1000 ratio, because 1000 kilo is 1 mega. So that's pretty much means that effectively all the voltage would be consumed by this one in darkness. So the voltmeter reading, when the voltage is measured across the R, so if we connect a voltmeter over here, we're basically trying to get the voltmeter over here. Now, other than writing a voltmeter, let me just get this part. Because we are trying to get a graph over time, how about I give you the name CRO? You have to understand that CRO is basically a fancy device to measure voltage. Fancy because it can do a lot of stuff. It can produce a graph and other whatnot. Whereas a voltmeter simply gives you a number. So let's say we're using a CRO to produce a voltage versus time graph, which makes it more visible or easier to understand or comprehend. So in darkness, this device will be pretty much consuming the entirety of the supply voltage because it is hugely bigger compared to the other one. That's for the darkness. In light situation, let me use red now. In light situation, the resistance of this LDR is 1 kilo ohm. Now, if you compare these two numbers, 5 kilo ohm and 1 kilo ohm, you'll see that these two numbers are very much comparable because there is a very beautiful 5:1 ratio over here. So, which means this supply voltage will be divided into 5:1 ratio. So, if we get the section value of this one, this will be 1 divided by 5 plus 1 multiplied by 1.5. How much do you get out of this? Have a look. Okay, have a count. 1/6 of 1.5. কত হয়?
0.25.
0.25 volt. Which means in brightness, this one is going to consume 0.25 volt, significantly smaller than 1.5 volt. So this is going to be consuming 0.25 volt, where the other part, I mean, this 5 kilo ohm is going to consume the remaining, which is 1.25 volt. So this is what's going to happen in bright light. This is what's going to happen in dark light. So if we do plot a graph of the voltage available across this R component, how does graph look like? You have to understand this part. For some duration, when the flashlight is on, the consumed voltage will become very small, 0.25. When the flashlight goes off, there is darkness, the resistance increases, and then the consumed voltage will spike to the maximum 1.5. So you will have 1.5 for the darkness, and then you have 0.25 in the bright light. As you do the flashing thing, your consumed voltage is going to bounce up and down between these two values. Observing the option choices, which one do you think is the correct response?
Sir, B.
B is the correct response. এটা কি সবাই বুঝছো?
B.
ওকে, ডি বলছো কেউ?
No, sir.
Okay, B is the correct response. আচ্ছা, now let me ask you this question. If you have understood this thing properly, for A to be the correct answer, what choice would you have to bring in this question? এটা একটু চিন্তা করো. This is a sort of reverse engineering. If you wanted A to be the correct answer of this question, what should have been our change in this question? The minimum change that you can do.
স্যার 1 কিলো ওহমসের জায়গায় অন্য কিছু লাইক হায়ার কিছু
কত হায়ার?
থাকতো।
Like higher than
স্যার
5 kilo ohm or less higher? It should be definitely,
higher than 5 kilo ohms.
it should be bigger than high 5 kilo ohm. That's exactly what I was trying to look for. Have a look. When the brightness happens, this voltage is showing a constant voltage of more than half, right? This half is over here. If this was given to become exactly 5, then this graph should look like 1.5, 0.75, 1.5, 0.75. So this would be available if the resistance of this component was exactly 5 in bright light. Since this constant voltage is much bigger, so if this value was significantly bigger than 5, let's say I'm gonna give 15 kilo ohm, then you could have get A as the correct answer. দেখো বুঝছো কিনা? It will drop. Visibly it will drop, but not so much. বুঝছো কি বলছি পোলামান?
স্যার যদি এমন হইতো মনে করেন লাইক 1 মেগা ওহমস এর থেকে ছোট একটু ছোট জাস্ট একটু ছোট তখন কি হতো?
Like 999 mega ohm.
আর একটু ছোট লাইক মনে করেন মানে মানে কোনো রেশিও নাই কম্পেয়ার করতে পারবো না 5 কিলো ওহমস এর সাথে। ইয়েস স্যার
It's still very large.
ইয়া শিওর।
So yeah, you'd still in darkness you'd still get full voltage across the one across the earth. It will consume huge portion of it. I mean, think about it. 5 kilo ohm means what? 5,000. 5,000 plus 500, 1,000. উপরে হচ্ছে 500, 1,000. এটাকে তুমি যদি বাই করো তোমার এই রেশিও হলো কত আসবে? ক্যালকুলেটর বসায় দেখো কত আসে।